Can we start? Okay. So today is July 14th, Tuesday, and no, Thursday. We're going to continue with the study of uncoupled roll motion. Okay, so last session, we analyzed the free oscillation after we have deduced the complete differential equation for roll motion. We kept only the terms which were involved in the calculation for free oscillation. And from there, we went on and calculated the natural frequency. And there was some relations that we could see with this solution with what the IMO states, right? For example, for small ships, they have a recommendation. So you could, with the period of roll motion, you could go on and estimate the GM, right? Because I don't know if you have experience, but when you try to do an inclining experiment, it's very, very, very difficult to have the ship to stay still. It's always moving because there's some wind, there's some current, ships passing by, and all of this generates little waves, and that moves you. And so the pendulum is moving like this. And if it is on a small ship, it's even worse. So in those cases, the IMO recommends or accepts to determine the GM using this period of oscillation. Okay, now, in this formulation, it is implicit a value for the virtual radius of gyration. And they have done some estimation, statistical estimation of that parameter, so we don't have to worry about that. But it's a good idea to have a formulation to estimate that, right? Because this parameter is it's not complicated. It's just, what can I say? It takes a lot of effort. And at the end, the exactness of your result is not equivalent, consistent, doesn't pay off all the effort that you have to make in order to keep track of these little masses and with these distances to the centroid, right? So eventually what we do is simply we use a formulation to estimate the virtual radius. So that's what I'm going to present. And then in this problem, roll, one of the big things is damping. See, you talk about roll and always ask about how did you do estimated damping, because it's a problem. It's a big problem. So we're going to explain one methodology. It's empirical, let me tell you, it's an empirical estimation of that, okay? And related to that, I'm going to give you an example for the assignment, for the next assignment, okay? More or less, so you have an idea of what's will happen. In the next session, there is one more topic, which is related to the excitation. This is another big thing to estimate, very complex thing to estimate. We're going to present a very simple procedure, which is explained in the class notes, okay? I'm going to include a correction factor in the slope to get what the IMO calls an effective slope, okay? And you don't realize these details, but in the IMO regulations for stability, it's in there. But we're going to apply independently in the procedure that we're going to present. And then that's it. So we have virtual inertia, damping, restoring is easy, excitation. So we can proceed and calculate the response, right? Remember, this is linear uncoupled, okay? And in the next session, next Thursday, you will do the test, and then you will have experimental results, and we are going to compare with your calculations, okay? So that's the agenda for this session and for the next week. Just to keep you in track, then you will have 3 sessions, right? Third week after the exam and half week, because in the 4th week, you will have an evaluation. So in these 3 sessions, we will present the material on irregular phenomena, right? So we need some statistics for that. And you will prepare also a short assignment on that. Okay, so that will make it. And then you will do an evaluation on that on Thursday. And then we will have 3 last weeks. And in these 3 last weeks, we have to basically, mostly what we do is check the advance of your project. Okay, the progress of your projects. Basically, that's what we do. Yeah, we have to explain some theoretical things, but mostly is how good are you going in your project. Okay, so more or less that's the agenda for the next 6 weeks. Okay, is there any questions about what I just explained, people? Is there any issue? No? Okay, then let's go on. Okay, here. So this was the last part of the last session. Can you check, can you confirm me that you can see my full screen, people? Can you see my full screen?
Yes, we can see.
Thank you. So this is part of the last session, and this is not in your class notes, but you can see it in Bhattacharya's book, chapter 4. It's in there. So it's a good idea, right? So for example, if you apply the stability code for IMO, and there is a criterion called the weather criterion, okay? And then you have to calculate in a very simple way an angle. And that angle, people, it's the response, the amplitude of the response, an approximation of the ship in roll when the ship receives waves from the beam. So it's in there in a very simplified way, but it's in there, right? So you have to calculate the period, the natural period, because at that condition, you have to calculate the excitation. They don't tell you that, but it's implicit in there. So when you calculate that is a long process, you have to calculate the period. Okay, so this is a good idea to check. You obtain the period, check, makes sense, go on. Okay, now let's go on now. So we're going to say a couple of words about the next component, which is the virtual radius of gyration. Okay, now formulation is in Bhattacharya, and this is chapter 4. This is specifically for ordinary merchant ships. Bhattacharya, it's a book which was prepared in the 70s. Okay, so maybe 40 years ago. It's an old book. So if you find a better estimation of this parameter, okay, this is the virtual radius of gyration of a ship, use it. Okay, otherwise, this is something that we can use. Okay, in this case, we have the CU. Okay, CU is the upper deck area coefficient. Okay, it's similar to water plane, but with the area of the deck, of the upper deck, not with the water plane. Okay, another parameter which is here is the effective depth. Okay, so this is very important. For example, when you have passenger ships, because usually in passenger ships you have many decks, right? So for example, let me do it in a small sketch here. So let's suppose we have something like this, right? And here I have another deck and another deck, something like that. So let's suppose that the flotation is about here. Okay, and of course you have all of these material which is away from G. Right. So that means that there is a lot of material which is located away from G. So you have to consider all of these, okay? And all of this is what they call A, is A here. Okay, so this is just another way to include this material in order to calculate an effective depth of the ship. Okay, and that goes in here. And you see that you include this, and this is going to increase. Okay, so this is a large, very large procedure. There are some options for this value of F. Is in that reference, it's all of this information. This CB, block coefficient, it's no big thing. This is draft. This is beam, of course. That's something. So this is specifically for these ships. Okay. Oh. If you have a different type of ship, then in that case, we can still use this formulation, but it's a better idea if you try to find another formulation for that specific type of ship. Okay. In this reference, there is another formulation, but for Navy ships. That's for ships from the Navy. It's slightly different, but I don't think it produces much of a large difference in result. Okay. The message is that you have these formulations specifically developed from, this is not an analytic, this is just empirical, right? So what you have to be certain is that you apply in the range of application. And in this case, the range of application is the type of ship. You have different formulations for fishing vessel, use it. Use it. The best recommendation I can give you is try to apply not one, maybe 2 or 3 formulations and see if the result. They are too far, then you have to think about why, try to explain differences. They are similar, take the average, and that's it. Okay, so that's that. So let's go now to the main topic of this afternoon. The main topic is damping. And you see here that I use the word estimation. Okay, because this parameter cannot be calculated analytically, definitely. Why not? Because in this process, we need to include the influence from the viscosity. The viscous effects in this case are very, very, very important. I'm going to write it here. Viscous effects are not important, are very important. So, yes, engineer, Dr. Rumen Paredes, he's our numerical hydrodynamicist. He uses a lot of CFD, but so far, we have to rely on empirical formulations deduced from experiments. That's basically, up to now, basically that's the main source of for our formulations for this parameter, okay? And I studied in Michigan, and in Michigan, this is the reference that we used to use, okay? It's, look at the title, State of the Art. State of the art. That was the state of the art in 1981. But some years ago, not many, 5 or 6 years ago, I attended a symposium in Lima, Peru. And there was a presentation from somebody from Brazil. And he was discussing the new generation of intake stability criteria. And they include what they call some failure modes, okay? Capsizing modes. And one of them is what they call the parametric roll motion. In that case, you receive the waves from the bow, right? From the bow. So linearly, there will be just this. You receive the waves from the bow. But if there is some relationship between the frequency with which you receive the waves and the frequency of roll, even if you receive waves in this direction, you can start rolling. That's what we call the parametric excitation. So he was explaining these new ideas from IMO. He was in one of the committees of IMO, and he said the only way what we can fight this problem is damping. So I raised my hand, Professor, that the problem is that damping is so complicated. Yeah, but that's what we have to do. How can we estimate that? And I asked him, Jimenez work? Yes, Jimenez is useful. That's Jimenez work, right? It was what, 30 years old work, and it's useful. Okay, so it's possible that we can find some newer formulations, but the basic idea is there. So that's why I think it's a good idea for you to experiment using these formulations. Okay, so I'm going to explain some details of that. For some reason, I scan it, so I have it, and I'm going to share it with you because I want you to do some calculation from here. Don't worry, it's not too long, but I want you to get in there and do some. Okay, let's go on. Now, one of the key contributions, okay, I don't think this is, we can call it Jimenez method, right? Because it was a group of scientists from Japan. I don't know why, but in general, it looks like the way they are, okay, they are like, they are very patient. Okay, so they can start and restart and do it again and try to solve until finally they get it right. And that's a lot of information in experiments, right? So Imeno is the name, but there is a group of people. And the other people that it's in this group, it's Ikeda. Let me write it here. It will appear in a second. So let me write it here. It's Professor Ikeda. Don't ask me for the first name, please. Okay? So one of the first contributions that they did was that they did a decomposition. Since this should be this should be decomposition. Anyway, you can correct. So they say the damping coefficient, okay, is the composition of several sources. These are the sources that they proposed. Is due to friction. Yeah, they do this, and of course there's some friction. Makes sense, right? But also, once you do this, there are some eddies which are generated. And these eddies are dissipation of energy. What are lifting? And lifting is generated when the ship advances with a certain velocity. When there is no velocity, this component doesn't appear. Okay? Generation of waves. Okay, this can be calculated using our concepts from chapter 2, potential wave, potential flow. So in this case, you work with the velocity potential function. With that, you generate pressure. With pressure, you generate forces. When forces generate moment. I did this calculation. Using finite elements, we solved this problem, a 2D problem. and I insist, potential. And finally, that's something that we should, as naval engineers, we should come out from the university thinking that at least for small ships, bilge kills are something necessary. Because it increases dramatically the damping coefficient in roll. Okay. Also, they declare, as you can read here, that this bilge kill coefficient, it's composed of 3 terms. Okay, this is the normal force. Okay, you have you have the section of the ship. You have here the bilge kill. The ship does that, right? When it does this, there is some pressure acting directly, normal to this surface. So that generates a moment which tries to avoid the motion. But also, on the whole, okay, because the presence of this, on the whole, there is some change in the pressure distribution, and that generates another way of damping. And finally, there is also some waves which are generated because of the presence of the Birch-Kill. So all of these three terms compose the influence from the Birch-Kill. Okay, and you see that here we have friction, here we have eddies, here we have friction. See what we had said before? The viscous is so important in this case. I mean, we can avoid including that. Okay, so I think that's the main idea here, right? Is that the damping is the composition. One of these terms is the wave generation, and that wave generation could be calculated using potential flow. All the other terms, they depend on the viscosity. They are very complex to calculate using analytical procedures. Okay, we have to rely either on laboratory experiments or lately in the use of CFD. Okay, so let's see some details about these calculations from Professor Imen. Okay, so first, it's something which is very, 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 very important in roll motion, is that when we have velocity, okay, the ship advances with velocity, the damping coefficient increases dramatically. Okay, and you see these results here. Okay, so the formulation, this is just formulations. Okay, if you apply the formulation from Imeno, right, here we have the influence of the velocity. Here you see this is the Froude number. How do you find the Froude number, Miss Astudillo? Do you remember the definition of the Froude number?
Velocity over gravity LPP square.
Root square, root square. Okay, good. So say, here you have implicitly the velocity, right? And here you have the summation, the combination of several of the components, okay? So here you see this line is basically horizontal. That means that the frictional coefficient, basically they do not depend on the velocity. The lifting, yes, because we said that the lifting is generated once the ship moves. But if the ship doesn't move, we have no lifting. Okay, the eddies is very interesting, okay, because it decreases. And at a certain velocity, basically it disappears. The wave is very interesting because as it changes the velocity, all the wave system changes because the waves are very related to the frequency, right? So when you have certain velocities, the waves are generated with a certain frequency and they increase or decrease. And that's why we see this waviness in here. And then these three components here are due to the Birch-Kill. This is the result. Okay, so if we consider, okay, only the wave generation, you will see this component is the only one. And for any velocity, you see that this component is very small compared to the total in general. So if we take this component to estimate the damping coefficient in the ship roll motion, and you're not going to get a good answer. Okay, that's why we have to rely on these results. Now, something which is very interesting is that when we start considering the case of, I mentioned before, this new generation of stability conditions, stability analysis, okay? They considered what they call a situation that they call dead ship situation. So what they do is they have a ship like this, velocity and the waves coming from the beam. What happens in this case? Since you have no velocity, you have the lowest value in damping. So in the calculation that IMO asks us to do, they are asking us to consider the worst situation. And the worst situation is to receive the waves from the beam and with the lowest damping coefficient. And lowest damping coefficient, of course, when we have no velocity. The ship has no velocity. That's why they call it dead ship, right? And that situation occurs when we have for some problems, we lost power, so the ship doesn't move, right? And when the ship doesn't move, the waves start heading, and basically they push it from the side until basically you start receiving the waves from the side. You lose power, reduce the damping coefficient, and usually the waves push you so that you start receiving waves from the beam. So that's the worst. If your ship is able to support that situation, once you start moving, you can increase the damping coefficient, so you reduce the response. And second, you can start changing the heading, so you don't receive waves from the beam anymore. So if you support, you do not capsize in this situation, in that ship, that means that in regular situation, when you can move and select the angle of heading, you are going to be okay. So that makes sense, right? And that's what Imenos presented us. Okay, so velocity in roll motion is extremely important. Else, another factor, another parameter is the frequency. Okay, in general, we couldn't expect that with more frequency, okay, we will have more dissipation of energy in general. And that's what we see here. Here we have frequency, but this is non-dimensional frequency, okay? Remember when you calculate the A33 and B33, there were in non-dimensional frequency. In this case, it's similar to that. But anyway, depends on the frequency. And here you have the damping. And you see that as you go to the right, increasing the frequency, basically all the components increase, basically, well, except the lifting. Because the lifting basically depends only on the velocity of the ship, right? So in this case, the Froude number is a constant, okay? Something which is very important here is that this parameter basically it's a function of the frequency. For this specific value, right, we have a jump in wave. Okay, so remember, let me go back here. You see here that for a certain value of the frequency, we have an increase in wave generation. Okay, and that's why they're pointing here, is that for a certain value of the frequency, when this non-dimensional period values 1/4, we have an increase in this wave parameter, wave down. In general, as we increase the frequency, okay, so we got more dissipation of energy in general. Okay, Imenos produced these empirical equations, right? So this is very long expressions with very strange numbers, strange coefficients, right? Many decimals, and we have to be very careful with the units and all of that, okay? You don't have to type that. It's already been typed. I will explain how to use it in a minute, okay? But there is one component which is very important, and it's the wave generation, okay? So they presented this formulation. A1 divided by X5 exponential and all of that. It's very, you see, it's extremely strange formulation divided by 1.44. Don't ask me why it is not 144 instead of 133. No, they just, they did was they generated a lot of information and they just tried to fit a curve on this information. Basically, that's what they did. Okay, so in this case, you can recognize the W because of the waves, and the 0 here means that no velocity, right? And to consider the advanced velocity, they included a formulation from Ikeda. You see this name? Okay, so they did some tests without velocity, then they did tests with velocity, and they determined, first they decomposed. They get the component of friction and wave and lifting and all of that, and they saw how was the change in this wave generation, just in this case, okay? And that's the result. You see that here, what they do is they take this value, they put it into here, and from there, they apply these parameters, and probably some of this will depend on the velocity. And at the end, you get a new parameter, W, waves, but no 0. That means that in this case, they are including the influence from the velocity, okay? I want you to use this parameter. So at the end, we will be able to calculate the wave generation, okay? Because you have to give to the program this information, okay? So we can go on and proceed. Okay, so this is something that is not in this calculation. You have to do it. So I want you to get into this report, get the formulation, interpret what parameters you need to calculate, and then you do the calculation. And you have to do this specifically for the case that we're going to do in the experiment. Once you do that, you're ready to do the calculation for your project. That's what we need, okay? We have to be very, 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 very careful because this is a very long process, very long procedure, and each one of these parameters has to be calculated independently, okay? So I need you to do this independently for each for any combination. Okay. Now, as I said before, okay, all of these components, in this publication at the appendix, there is a small program. It was written in Fortran. So we implemented here, we compile it and make it run. So it's available to you, okay? So you don't need to type that. You need to calculate this, okay? I'm going to ask you to do this calculation and also a calculation for using a formulation which is in the Bhattacharya's book. Okay, these two formulations. That's independent work. Okay, and then after you take this value for the wave generation, okay, you prepare a file, a text file. Okay, and this is a typical text file for that. Okay. This is a calculation we prepared a couple of years ago. In this case, we were trying to determine or to compare the influence from a Bilge-Keel and from an active roll control motion. So we needed to do how much influence has the Bilge-Keel. Okay, so this is the data file. So can you read here? People, can you see details of this file, people? Ms. Vega, can you see? Okay, so here, see, this is something that is quite useful. On the right-hand side, you see that this is the name of each one of these values, of the variable of each one of these values. So we have length, beam, draft, volume, CV, CM. And then here we have viscosity. Just since viscosity is so complex, in some cases, we have some results from tests. But these tests, we have to be careful because in some cases, for example, you develop a test in Michigan. Usually the water in Michigan is very cold, even in summer. So that means that the temperature probably here is not 22, maybe around 10. So the viscosity will change. So, and these 10 degrees can make a big change in a model. So we have to be careful. That's why I put it in this. This is the fruit number. This is the number of stations that we need to consider. Okay. In this case, this is the number of fruit numbers that we have to consider. In this case, it's only one, so one velocity. I was analyzing the ship moving with one velocity. Okay, this is the information for the stations. Okay, so for each one of these stations, you need to include the number. Please, the 0 here is the aft perpendicular. But it's information. Okay, so be careful. 0 station is in the aft, not in the forward. Then we have BX, beam, sectional coefficient, and draft. Okay, so that information is to calculate the sectional coefficient of damping at every station and then integrates it. See, it's basically doing a trip theory analysis. Okay, down here, okay, this is the width of the bilge keel, 67 centimeters. So it's about this. It's a good, because there was a passenger ship. The problem with this ship was that they were having complaints from the passengers because the motion was too small, too large. So they take them to vomit very easily. So they installed a large bilge keel, 67 centimeters in wide. Okay, this is the position, right? From 439 to 10. So from here until here. This is the number of stations. Okay, and then down here, this is the information about the specific condition that I want you to calculate. For example, this is OGD. This is typical. This is the distance from the flotation to the position of G. This is the period where you want to analyze. Remember, period is the opposite of the frequency. This is the angle that you want to analyze. Remember, this is very easily to get into the nonlinear range. Okay, so in this case, this value 0.073873 corresponds to 5 degrees. So this is radians. Okay, so what I did, you see that this value, this is the tau is the same, the OGD is the same, the only change is in the amplitude. Okay, so all what we're doing, we're to calculate how changes this parameter, okay, the damping, using the, depending on the amplitude. So what we did was we generated a curve with the variation of the damping coefficient. It's not constant. It's not constant. And what we did was we did a simulation. Okay, so you have a certain velocity, get into these values interpolated and get this value to do the time integration. And then as the time goes by, you change the value and you are taking different values from these results. And here, okay, here for this condition, you need to input WO. WO, what is that? That is the wave generation damping coefficient for no velocity. So what they do is they take this value. Internally, there is a procedure to estimate the influence of the velocity. That's why you're given this fruit number. And from there, they calculate the value of the wave generation damping coefficient at a certain velocity. Calculate all the other coefficients, add them up, and then integrate over the whole thing. This is for the whole ship. This is for the whole ship. Question, people, so far? Oh, and here, this is part of the result file. Okay, you get something like this. Here you have part of the data. Up here, we have all of this just to check. I didn't want to present this. This is the result. And you see that you have here friction, wave, eddy. And here is the combination of all of this. Okay. And the eddy starts increasing. Lifting is constant because it depends on the velocity. Bilge chill increases because it's nonlinear. So as you increase the, each one of these calculations is for a different value of amplitude. Okay, so for each value of the amplitude, you have a different result. You see that this is not constant. Okay, so remember that here you have 5, 10, 15 degrees. So we have all of these values according to the angle of rho. So this is what I want you to do for the model that we have at the university. And I want you to do this calculation independently, right? Any questions so far, people? Any questions? No? Okay. Let's take a break here, 4:53, and we return. We did some years ago a thesis, some tests here in our show the results when we compared results from this test with a formulation which is close to this one here. It's not exactly the same. It's more modern, but it's the results are interesting. Okay, so Miss Kinde, would you please stop the recording?